And so another, so if you believe that any distribution with any distribution that has the same moment generating function has to be the same, then you should also believe that if two distributions have all the moments are the same, then they have to be the same. Because if all their moments are the same, then the moment generating function is the same, because by this Taylor series expansion. All right. And let's calculate a few more moment generating functions. So these moment generating functions are very useful, and for a lot of people who are working in this area, it's best to just memorize some of these moment generating functions, because then when you spot it somewhere, you see, oh, it's probably this distribution that's playing a role here. So let's calculate it for a person. Let's do this person lambda. The x is person lambda. Let's calculate the moment generating function for that. This is the expectation is the 2x. And so what is the formula? K equals 0 to infinity. Tk is e to the negative lambda, lambda to the k of k factorial. E to the negative lambda, I can take that out. Doesn't depend on k. E to the t times lambda, that raised to k over k factorial. And now we know that this is just the Taylor series expansion of e to the x. So this, since we know this, we get is just going to be e to the lambda e to the t. So lambda e to the t is right. So this is a moment generating function for a Poisson distribution. And if you want, you can calculate what this is and then find the mean. This way. You can do this right away. The derivative of that is e to lambda e to the t minus 1 times lambda e to the t. So evaluate that at 0, what do we get? My t equals 0. So it's e to the lambda. E to the 0 lambda. So this is the expected value from x equals this. You can do the same thing to calculate variance. First calculate the second moment. So you differentiate that twice at t equals 0. That the second moment, you can use your variance formula. Let's move on. Okay, so let's do a continuous distribution. Let's say function x is exponential lambda. Let's calculate moment generating function x. This is tx times lambda t minus 1. All
keep differentiating, you're gonna keep ending up with one.
No.
Okay.
That's, if you keep differentiating, so define exponent value x squared, differentiate this again, and then set t equals 0. That is not lambda,
Okay.
right? In fact, it should be lambda squared plus lambda.
Okay.
Yeah, so calculate this. When you set this equal to 0, you should get this. And then plug into your variance formula, you will get lambda. All right, okay, exponential. Okay, now here's something with exponential. If t equals lambda, then I have e to the 0, right, which is 1. If I integrate 1 from 0 to infinity, that's infinity, right? Okay. So clearly, if t is greater than lambda, I get something even bigger than that, right? Okay. So I have a problem. When t is greater than or equal to lambda, this is not defined. Okay. So my moment generating function for exponential is only defined for t less than lambda. So this is defined, undefined for t greater than lambda. So I'm going to do this integration assuming that t is now less than lambda. When we integrate this, I get e to the t minus lambda x over t minus lambda from 0 to infinity. Now if t minus lambda, if t is less than lambda, so when I'm continuing here, I'll say for t less than lambda, I can do this calculation. Mx of t, for t less than lambda, mx of t is this. If t is less than lambda, t minus lambda is negative. As x approaches infinity, t minus lambda times x approaches negative infinity. E to the negative infinity, that's 0. So I get 0 minus, when x is 0, you get e to the 0, which is 1. So you get lambda over lambda minus t. So for x, which is exponentially distributed, your moment generating function is lambda over lambda minus t for t less than lambda. And this is undefined for t greater than lambda. So for your moment generating functions, they need not be functions that are defined for all t. So you need to determine the domain of that function. All right. All right, so we'll calculate the normal distribution and stop there for today. And then we'll talk about properties of moment generating functions next class. Let's start with standard normals first, and then so the moment generating function for standard normal random variable, the definition is E expectation of E into C. So this is just integral from negative infinity to plus infinity. e to the t little z, which is the density function, is 1 over the square root of 2 pi e to the negative z squared over 2 dz. So this gives me 1 over the square root of 2 pi e to the negative, that is z squared, minus 2tz. What I'm going to do next is complete the square. So for that, I'll add t squared and subtract t squared. I'm going to write it as z squared minus 2tz plus t squared minus t squared. So what does this give me? Square root of 2 pi e to the negative 1/2 z squared minus 2tz plus t squared. Minus t squared gives me plus t squared 2. So here this has become z minus t squared over 2z. So e to the t squared over 2, I can pull that out, and this is now e to the negative 1/2 z minus t squared. What should that give me? Well, recall that if this was normally distributed, what is its density function? It's 1 over square root of 2 pi sigma e to the negative x minus mu square over 2 sigma squared.
Oh my.
So what is this stuff looking like? This looks like the density function e to the t squared over 2 let me write it as the density function of some random variable where y is normal. And guess what the mean is? The mean is t, and the standard deviation or variance is 1. There's 1 here. This is exactly the density function, 1 over square root of 2 pi sigma. If sigma is 1, mu is t, then this is just the integral of the density function of a normal random variable with mean t and variance 1. What's the integral of a density function? Integral from negative infinity to plus infinity?
1.
It's just 1. So that just gives you. So that is why I was trying to complete the square here so that we can write this as the integral of the density function of some normal distribution. All right. So for standard normal, we have 2. Now for any normal random variable, what is its moment generating function? Well, here's one of the properties of normal distributions. If I take a normal random variable, subtract its mean, divided by standard deviation, is the same as a standard normal distribution. So I can always write a normal distribution with mean, mu, and variance sigma squared as sigma z plus mu. So sigma times a standard normal random variable plus constant mu. So I'm interested in the moment generating function for any normal distribution. This is the tx. This is e to the Now I replace x with sigma z plus mu. This gives me expectation of e to the t sigma z plus t mu. Now e to the t mu, that's just a constant, so I can take it out of expectation. Okay. Now my expectation with respect to z, sigma times z. This is just the moment generating function for this random variable z at the point t times sigma. So this is e to the t u, the moment generating function moment generating function of the standard normal at the point t times sigma. So now let me use this thing that I've derived, and I get e to the mu times t times e to the 1/2 this thing squared, which is t squared sigma squared. So this tells us the moment generating function for a normal distribution is e to the mu times t, the mean times t, plus 1/2 the variance times t squared.
I'm not even going to put that on my formula sheet. That's just intuitive.
Okay. It's also very important, so you might want to.
Just in case. Just in case.
Yes, just in case on the day of the exam it is not intuitive enough. Okay. So you definitely want to know this. So this the moment generating function for most known distributions, it's good to know what they are. Or if it looks vaguely familiar, that's a good idea. You can always look up what exactly the form is. But the normal distribution appears literally everywhere in probability. So recognizing the moment generating function is, remembering it is important. So e to the mean times the t plus 1/2 the variance times t squared.
That whole thing is the exponent?
Yeah, so that's the whole thing.
The whole sum.
So very important.
If we were to approximate binomial using normal, like how we were doing in chapter 5, would the moment generating functions work as well?
Okay, so approximating binomial, in fact, that's going to be a special case of the central limit theorem, which we will get to. So, yes, and this whole idea, as I said, we're going to use moment generating functions. So, yes, if you take the sum of Bernoulli's, sum of Bernoulli's is a binomial. Okay? So, basically, you take the binomial formula, put it there, and, change your n, let n go to infinity. You have to normalize, of course, so divide by square root n. You will find that it will start to look like this. And, okay, so if you, just looking ahead, that was p to the t plus 1 minus p to the end, right? What has something like this and something to the end? I mean, remember this formula, and this is going to play then a role. I mean, limit. So clearly you already see that this is appearing in the right forms. Because eventually it'll have to be scaled, and some scaling will appear from somewhere. Okay? We will get that later. But notice this fact, that 1 plus a over n to the n is e to the a. So if we're looking for the moment generating function to become something of the form e raised to something, then clearly you see we'll have to at some stage use a formula like this. Okay, so that's it for today. Next class we will talk about other properties of moment generating functions.